Is it clear to you?
Yes, it is.
Clear,
Yes,
sir.
sir.
Yes, sir.
Okay.
Yes.
Okay. Let's start. My topic is today we'll cover the functional nanomaterials and in applications for energy device. Okay. So in that talk, first I'll take my research specialization and background, and then I'll tell about the introduction part of the nanotechnology and the applications of nanomaterials which we have synthesis in our lab for the particular purpose of application for the energy device, like photoelectrochemical water splitting, perovskite solar cells, fuel cells, and multifaceted composites. So in the topics, first my background is I did BTech from HIT, then MTech Jadavpur University, PhD from IIT Kharagpur. Then I did two postdoc. One is from South Korea, SKQ, and another is USA, YU University. So here, if you see, synthesis define types of nanomaterials like nanostructural sphere, nanorods, nanofibers, nano clusters. These types of material we use to synthesize in our laboratory, Calcutta University, and we applied after synthesis this material for making the energy device. Energy device means means fuel cells, water splitting, hydrogen generations. You all know nowadays renewable energy is the most important in the research part because the energy is crisis to overcome the crisis energy to overcome the problem. We used to apply these types of nanosynthesis material for this purpose. Now, if you see the figure, my topic will divided by the 4 parts. Initially, I'll discuss the low power consumption memory device, multiple state memory device, and then what is multiple memory device and how it's applied nanotechnology field. Then electrolyte water splitting for making the clean energy hydrogen generations. Then after that, I will discuss the perovskite solar cells for low cost making environmental friendly solar cells. And finally, I will discuss the fuel cells, which directly convert the chemical energy to electrical energy. So as introduction part, as you all know, what is the nanotechnology? Actually, nano means that occurs at 1 to 100 nanometer range. It may be 1 dimension, 2 dimension, 3 dimension, like that. So it is an interdisciplinary subject which combined to the science and engineering interconnected each other. And is occurred in the manipulated atom or molecular levels to make a new devices. So it has actually 2 parts, nanoscience, which tells about the nanomaterials, and the applications of the technology of the nanomaterials is called the nanotechnology. So why nanotechnology? Nanoscience is important. When you go in the smaller size of the material, then you'll see the unique property evolve in the material. Different types of the unique property comes from the material. That property gives actually different types of devices for making the devices what we want for the particular our society's applications. So we used to tune this smaller size, nano size, and we tune different types of property what we desire from for the applications. So for nano fabrications, it has the 2 part. How to fabricate the nano? First is top-down fabrication, what start from the large material and bring it down to the nanoscale, and another is from the bottom to up nano fabrication, that from smaller size is made little bit larger. That means the atom level to up to nanostructure level. So by these 2 techniques, we used to make the nanomaterials in our laboratory. So here now I am starting my work. Before starting, after synthesis in nanomaterial, we used to prepare the multiferroic memory device, which consume the low power energy. So what is, before starting, what is multiferroic? Multiferroic means one materials which combine 1 or 2 of these property, which is showing here, elastic, magnetic, and electric. If any material is having combined of these 2 material, that called the multiferroic material. So why it is important? Because if one material having these 2 property, it can be applicable for the memory device for read and write. if it is right by electrically and read it magnetically, then power consumption will be very less. Nowadays, whatever hard disks we available in the computer, that is magnetically made, but so that it consumes the high energy power. But if you replace this device with these multi-ferrous materials, then the power consumption will be very low. So it is one of the material synthesis process and applications for this low power consumption device materials. So if you see the single phase multiferrous, there is a lot of single phase multiferrous, where is most important is perovskite material, which having the structure of AbO3. But it is having very weaker magnetoelectric voltage coefficient. This voltage, that means 1 to 20, it is varying. It is actually most important for the low power consumption memory device. And these single phase materials is having wide varieties of transition temperatures. So the overcome this drawback, we used to prepare the composite material. Composite material means two materials combined in a composite phase, where magnetic property and electrical property confined in the composite phase. Okay. So if you see different types of composite, here 1, 3, 2, 2 or 0, 3 type structural materials. Hello. Structural materials is available in our system. So if you see the 1, 3 type structural materials, so it's having the problem of leakage. And for laminated structural materials, it's having the camping effect. So our target was to make the 0-3 types structural material, which having the high magnetoelectric coupling. This magnetoelectric coupling shows that the memory device which consume the power energy high or low. So material selection sections, we initially first optimized a parameter. Optimization parameter for selections. For piezoelectric material, we select the lanthanum doped lead titanate. Why it is lanthanum doped lead titanate? This material is having very good ferroelectric property, dielectric property, and electro-optical property. And for ferromagnetic material, we choose the cobalt iron oxide material because it is having very high magnetostatic coefficient. So after that, we total optimize the process parameter. Make the sol chemistry, optimization of the lanthanum content in the lead titanate, and finally optimize the synthesis condition and the volume fractions of the constituent phase. This is the process to synthesis the material. How to synthesis? We fabricate the thin film by making these two salts. One is lanthanum acetate trihydrate salts, and another is cobalt nitrate with solvent. So after making it, this is the stable salt we prepare. We change the percentage of the CFO amount in the PLT15 matrix from 10 to 1 volume percentage. You see this is the transparent stable salt we prepared. Then from this salt, we prepare the film. After making the film from spin coater, we dried and thermally heated. Then finally making the film, we check the structural analysis of this material. By the XRD, we confirm that all element of CFO and PLT15 presence in our thin films, but we observe slightly the peak safety is there. It is because of the lattice diffusion of the material inside the lattice. So next, we have done the characterization scanning electron microscopy. In case of the scanning electron microscopy, we confirm that all element that CF, CFO, PLT all are present in the material or not. We confirm that all material presents in proper compositions. And for the ferroelectric and magnetic measurement, thickness is very important measurement part. So in the same cross-sectional analysis, we confirm this is having the electrical property. We use impedance analyzer, LCR, and electrometer, so checking the electrical property of our thin film. So in case of the dielectric constant, we observe with increase of the cobalt iron oxide in PLT15 matrix, after certain level, the dielectric constant is increasing then suddenly it is decreasing. So we optimize the percentage of the cobalt iron oxide in PLT matrix, which is around 5 to 6% volume, and after that increasing is give the leakage property. So in the dielectric case, we proved one model that is showing the loss tangent and dielectric property and the percolation values of the material. So here, if you see the cross section, after increasing the CFO, you see the cobalt iron oxide is increasing. Here is suddenly diffusing in the bottom. So after that, it is receiving the leakage when CFO is increasing in the matrix. So these are the loss tangents of EIS analysis. From here we confirm that this is having the good ferroelectric property. Ferroelectric means that is the ferroelectric loops, which is showing that is having good capacitor value. If you see the last one, it is having the very leakage problem. It is due to high concentration of CFO. In here, we confirm that the nearly 6% of the CFO is giving maximum polarizations in the ferroelectric properties. And finally, another is butterfly loop. Is indirectly showing the how much capacitor is have. We got the very good capacitor by optimizing the CFO compositions. And here we prove the model, one model, DC conductivity and other things. So polarizations model, we prove that our material is valid, this model. Finally, as two material is combined is one other, so one electrical property we already checked. Finally, the magnetic and magnetoelectric property. In the magnetoelectric property, in the magnetic part, magnetic hysteresis we got from the squid. Here we have observed that increase of the cobalt iron oxide in case of in matrix of the PLT15, the magnetic properties, saturation magnetization, remnant magnetization, all are increasing with CFO content. So here, finally, this is the output result of our material, which is showing it is having good memory device activities. That means the magnetoelectric coupling. We got the coupling around 200, more than 200 millivolt per centimeter Oersted, which means it is tuning combined with magnetic and electric property. If you see these equations here, this is the magnetic inductions with output electrical voltage. So giving the magnetic inductions, it is giving very good output voltage. So in case the memory device, we conclude here that using a hybrid sol-gel route, we have synthesized the PLT15 and CFO composite, and we optimize the percentage where it's showing the ferroelectric and ferromagnetic growth property, very good property, and then finally this 03 types of piezoelectric material is showing this very high magnetoelectric coupling, which is nearly 250 millivolt per centimeter Oersted. So here, finally, if you see, when you measure a ferroelectric loop, the radiant all instrument which is available in the market, that is very costly, more than 10 lakhs or above. In our laboratory, we fabricate the same instrument in very low cost, below 10,000. So how it's done? You see this short hour target where the capacitor on reference capacitor and the ferroelectric material is there. If you follow this circuit, and finally, if you look here, one is DAC cut, which is interfacing with the computer, and here is the thin film. Thin film is showing the output result, and this is the short-hour circuit, which circuit we fabricate inside this system. If you follow this total with the capacitor, finally, we interfacing with the lab view, we check the data. Then, if you see, this is the happening in the top part of this lab view program. Upper part is showing the output voltage, and lower part is showing the input voltage. So if you run after doing this program, you see first you run, then save this program. Here the first curve is showing the output voltage, and second curve on the top one is showing the input voltage. Then you save the data one by one, input voltage, then output voltage, then run it. So you see in our thin film, it is showing the very good ferroelectric loops. That means it's having the very good ferroelectric property. So these types of device everyone can make in our laboratory, in your laboratory, in a very cheap cost. If you want to purchase this instrument, it costs more than 10 lakhs, but you can fabricate this instrument below 10,000 rupees. So this is the initial part, that we fabricate the instrument for the purpose of multiferrous devices. So this is the first part of my topic. Now I am going to the another part, which is hydrogen generations. Hydrogen generations. As you know, the hydrogen is very clean energy, and it is very costly to produce. But we produce these hydrogens by water splitting with using the light. So I'll discuss how hydrogen produced in our laboratory in very low cost. This hydrogen is actually very useful for fuel cell purpose, fuel cells which is giving the chemical energy directly to electrical energy. But the hydrogen storage and hydrogen generations of the fuel cells is very problematic. So our target was to get the hydrogens after splitting of the water. So in case of the water splitting, minimum voltage required 1.23 volt for to split 1 mole of water. So in case of the 1 mole of water splitting, the catalyst is also very costly, and it is required the power also. That's why we reduce the power. We use the different types of working electrode. In that case, in water splitting case, we synthesis hematite material for working electrode purpose. And for in the topmost, the surface modification, we use the perovskite to perovskite material, which I am coming here. Just in case of here, our target is to make a semiconductor material that having the appropriate band gap that can overcome the aqueous solutions electric and develop a energetic cool out semiconductor electrolyte. So if you look this water splitting setup, you see that in a cathode part, hydrogen's bubbles will come out and the oxygen's bubble will come out in the anode part. And if you attach this setup with the battery, the minimum splitting voltage required 1.23 volt. So our target to fabricate this anode and cathode with a perovskite material which having the light absorption property with giving the electric current from absorbing the light, and that current reduce the induced voltage of the battery. That means we don't need to supply 1.23 volt. It will come down slowly in the below 1 volt. So this is a process. If you give the light here in the anode part, the H2 oxidized, photon catalyzed. Then finally, in the cathode part, in presence of the catalyst, hydrogens with ionized and it's react with the water. Then it's give the hydrogens and oxygens. This is the working principle of water splitting. This main important here is band gap. When we selected the material, that band gap should be less to overcome the electric light. That means when you pass the UV visible light, it should overcome the band gap energy of the material. So selection of the band gap, particularly fixed band gap material, is very important for this water splitting applications. So you see that in the band gap what is band gap here? That is the distance between the conducting band and valence band. So in case of the requirement of the photocatalyst material, the band gap should be greater than 1.23 electron volt, which will be sufficient small to make efficient use of solar spectra, and it should be high crystallinity to give the unique property and should long-term stable here. Then benchmark of this experiment, first material we should target for commercialization is which is having the 10% conversion efficiency and current density up to 10 to 15 milliampere per centimeter square. But in our laboratory, photoanode characterizations, band gap energy around 2 electron volt, strong optical absorption property required here, high electron mobility required here, and the cost effective is most important part. So for this working electrode photocatalysis, we have to follow this triangular diagram where you see all the dependent parameters are correlated internally with, that means the surface doping, crystal growth, heterostructure is interconnected each other. So give the high electricity with using the low light intensity. For selection of the material, if you look at the table, you see the FeOT, mane iron oxide, that's having very less, very low band energy. That means it is very useful for photocatalytic applications. So other advantage, disadvantage of this hematite is having the short diffusion length, small charge transport, low hydrogen demolition rate, and visible light absorption coefficient is having very low. To overcome these problems, also it having the advantage that the band gap of this material of the variable dry precision figure, it is fixed, and theoretical conversion efficiency can be reached up to 12.9. So our strategy here, if you look in the theoretical, you see the hematite may give up to 12 joule, 12 milliampere per centimeter square current, and it is having the low voltage applications. But if you see the current which is standing here up to 0.8 volt. So we can improve this part by putting the morphological control. If you tune the morphology, then you see output current will increase, and then if we tune the surface chemistry, then applied induced voltage will be reduced. So these two parts we focused to control the optimization process of this system. So our first attempt here to enhancing the electrical conductivity, band gap modifications, improving the crystallinity, and the increase the carrier density space. So here we dope the cobalt doping to tune the band gap and increase the carrier density in the space-charged regions. The next attempt to modify the surface, lowering turn-on onset potentials, as we have used here, the perovskite, two perovskite materials, MaPbI3 and PbTiS3. So this is the electrode preparation process, where if on the FTO glasses we have done this, we thin film analysis, thin film preparations, where we polyethylene amine deposited by spin coating techniques, and then after is dried and make a solid thin film. So this is the process where you see the sol, a stable sol will be prepared first, and then this nano paste coated on the FTO surface uniformly by doctoral bedding. Then on the top of the surface, we deposited by spin coating techniques this sol, CO sol and Fe sol, and finally for surface modifications, we coated on the top of this by these two perovskite materials. So this is the last 5 and 4. This is the actually working electrode we used for water splitting applications. So in same case, before starting, we have to characterize our thin films. X-ray done for the structural analysis, UV spectra for optical property measurement, atomic force microscopic used for surface analysis, and solartron photostat for measuring the photoelectrochemical property of the material. So here, if you see the XRD structure, so all the material present in the proper impurity is not there, and finally we check the crystal size structure, that is, it is around 25 to 30 nanometer. So this is the structural elemental analysis, where all the element presence in form of the CO, Ti, Fe, CO, Cu we checked by TM microstructural analysis. And this is the AFM analysis, which shows the surface topography, where the surface roughness is more or less uniform. And optical property, in case of the optical property, we tune the cobalt iron percentage on the film of the TiO2 and FeO3. And here, if we check the band gap, we optimize the band gap of Ti by doping cobalt 3% is showing 1.96 band energy. This is the setup. You see the thin-edge flags where counter electrode, reference electrode, and working electrode are connected each other with a potentiostat, with a confined without putting the light. And one part is it is open in the light. So in the photocatalytic measurements, which showing the degradation of the methylamine in presence of the light. If you see, this is the concentration measurement of the methylamine, and finally we check the reaction kinetics. We show the which shown the 3% cobalt give the maximum kinetic rate, and the light absorption property is maximum in 3% cobalt doping composite films. So this is the current density measurement. Current density is reached around very good in case, and we optimized 3% is maximum current density giving using this potentiostat, and is giving 3.04 milliampere per centimeter square. So here photon conversion efficiency we got 1.72%, which is showing the how much photon converted to the light. So here the stability we have checked. We check the 5 hours, up to 5 hours, our working electrode is working properly without any deteriorations. So here, if we take the Faraday efficiency, that means what amount of hydrogen generating with comparing to the theoretical value is giving the 95% efficiency. That means loss of the systems is very less. So in case, if you see the literature, we are standing here up to here, giving the 3% cobalt doping. So here, the next step we go surface modifications by putting this TiO2, PbTiO2 perovskites, these two material to overcome the current literature's drawback. So in case of we synthesis these two of perovskite material, then finally we have done the XRD. We check the phase, all the phase present in the material. Then we check the crystal size structure, which is nanoscale level. This is the same analysis of the surface of these two materials, that is 10 to 20 nanometers uniformly distributed in the matrix. Then we have done the AFM analysis, where surface roughness is uniform in everywhere. Then we measure the band gap of the material, which is giving in the MAPBI3 1.6, that is reduced much better and compared to the PBTISG. Then we prepared the solar cells, which is having the AD top electrodes and the FTO bottom electrodes, and the middle we uniformly distributed the cobalt doped Fe2O3. You check the band alignment natures of the systems, and finally we check the efficiency of the materials. We check solar cell efficiency giving 3% cobalt doped. In case of the MAPBI3 is giving nearly 4.3%, whereas PBTISC is giving 2% efficiency. That means methylamine lead iodide is the best material for the solar cell here. And then finally we check the stability. In case of the here also we check up to 5 hours, the stability remains same. So here the comparison of the Faraday efficiency, nearly 95% efficiency we reach. That means the loss of the material is very less. So here is the finals for applied bias photon to current of current efficiency ABP, which increased 2.4% achieved in case of the MAPBI3 and 1.88 for PBTIO3. That means initially it was 1.7 and it's increased up to certain level 2.43. And finally, solar to hydrogen ratio conversion, that means solar radiations convert to hydrogens, the efficiency is giving for MAPBI3 2.43%, which is very good for comparing to the current literature. So this is the comparison system of the STH ABP value. If you see the theoretical value, it is giving nearly 2%, but theoretically it can be reached up to 12.9%. So if you see this system here, you see one video where a reference electrode, counter electrode is there, and working electrode. Here, hydrogen is generating in presence of the light. You see the bubble forming inside hydrogens, and it is storing hydrogen in here. So you can it is visible clearly that the hydrogens bubbles is there inside of water. So after storing these hydrogens, we measure the how much amount hydrogens stored after certain time. So in case of the water splitting, photocatalytic water splitting, what we have done, we have prepared the thin film, two types of thin films by cobalt doping. We optimize the cobalt percentage of the material, which is 3% cobalt doping hematite photoanode, and hybrid hematite film that porous nanostructure for photon harvesting efficiency very good, and this efficiency reach up to 2.43%, but in theoretically it can be reached 12%. After reaching the 12%, this instrument will be available commercially. Then some drawback is there to overcome these problems. That is the future plan of this research to enhance the stability by stopping the iodine formation because of degradation happening in the systems, optimization the necessary thickness of the high performance, and the light source should be set to the simulator at the fixed level, and finally controlling the temperature fluctuation by activating cooling systems. So this is the second part where clean hydrogen generations from water splitting is available by using the perovskite applying the perovskite nanostructure material. Now the third part I am coming, the solar systems, solar cells. We used to fabricate the solar thin films using the nanoparticle, particularly perovskite materials. We replace the lead, which is hazardous material in this case, by the tin, which is very environmental friendly. So these types of laminated layer we prepared on the surface of the glass and FTO surface, where the whole transfer layer will be there. In the top, the metal contact will be there, and in between, the perovskite layer and electron transport layer will be present. Nowadays, the efficiency of the solar cells is reached up to 22.1%. But for replacing the crystalline silicon solar cell, we have to reach above 30% efficiency for commercializations. So in case of the efficiency record in the solar cell, you see suddenly after 2006, perovskite solar cells is increasing the efficiency day by day. So that's why researchers are very attractive for this perovskite material for the applications of the solar cell purpose. This is the curve of the efficiency which is increasing day by day for the all perovskite materials, thin film technology, solar cell, crystallization cell, and organic PB organic cells. You see the perovskite materials, which is blue, after 2006, it is increasing very rapidly. So, but the problem here some of the hazardous material like lead is present. So researchers target to replace the lead by the other material. In our laboratory, we replace the lead by SN, and we check the efficiency or other factor of the solar cell material for commercializations. This is the synthesis process. At the stable salt, we prepare changing the SN percentage of the material. Then this is the fabrication process where the cell has been fabricated using spin coater techniques after ultrasonicated and on the FTO surface thin films. Then this is the setup where this is photovoltaic performance measured by solar simulator. Then this is the spin coater where the spin coated. Then after spin coating, heating is required. Then finally, contact prepared on the top of the surface for making electrical contact. This is the XRD analysis of this two film, where it is shown that the SN is conformally distributed in the matrix in the PbCl3. This is the nanostructure material of the same image of this ammonium lead chloride based perovskite, which is uniformly distributed in the matrix of the surface in nanoscale level. So here you see the nanosphere with big band gap, and here if you see the nanosphere larger size then morphology, you check this is the defined types of morphology is coming with tuning the SN percentage of the material. That means something nano rod is coming, nanosphere is coming, different nanostructural material is coming, just only tuning the percentage of the SN doping. So finally we check the electrical property of the solar cells. If you see the SN percentage 20% is giving the maximum efficiency of the solar cell, that is the 2.484, around like that. And with increasing of the SN, it is deteriorating and it is reducing up to 3.22. That means it is having the leakage problem is increasing with increasing the SN percentage. So in case of here, we conclude that the up to 20% SN depositions is giving the maximum efficiency, and we replace the lead up to 20%. After that, the cell performance is deteriorating. So this is the another part where we have fabricated the solar cell systems and we check the solar cell performance. Then finally, last part of my presentations where I'll discuss the fuel cells. How fuel cells work, you know. This is the hydrogen generation I already talked about, the by water splitting. We used to use this prepared synthesis splitting hydrogen used in the fuel cells, particularly proton exchange membrane fuel cells. If you see the diagram, hydrogen is coming and one side, and another side air or oxygen is coming. Then in presence of the catalyst, PT catalyst, it react each other. Then finally water produced and electricity produced in the top. So this is the mechanism, working principle of the fuel cells. So we used to splitting hydrogens from water, and that hydrogen to use for the fuel cells electricity generations. So in the fuel cells, electricity, what are the drawback in the fuel cells? First, it is actually very costly because of the catalyst, because PT catalyst is always cost. And one of the major problems here, that is water generations. That means the side product of water accumulate on the surface of this fuel cells membrane. So we have to overcome this generation, otherwise proper reaction will not happen in the interface. So for this purpose, properly working electrode we have to prepare, which having the high hydrophobic property and which repels the water molecules that will not accumulate on the surface of the fuel cells. So here, if you observe, the different types of fuel cells are there, particularly defined with defined membrane they have used, AFO, PFO, NFO, SOFC. But in between all the fuel cells, proton exchange membrane fuel cells is very important because it is working at the room temperature and also it is low cost. But in case of the fuel cells also, we used the Nafion membrane, which is very costly. So here our challenge was to limit the material base to constant the fuel cell systems, and our approach is to discover the next material to which replace the PT material, which is very costly, and modify the improvement performance of the fuel cells. So what are the possible criteria? First, the high ionic conductivity required in the working electrode part. Good mechanical stability required, and it should be low cost. For this purpose, we have to fabricate proper working electrode. So here, four basic elements are in the fuel cells are. First is anode. Anode is negative of these fuel cells, negative charged fuel cells, and cathode another part. So both these anode and cathode we used to fabricate in our labs by low cost using the cloth of the carbon dust. On the top of the carbon dust, different types of thin film nano composite material deposition techniques. And then important is electrolyte for the proton exchange membrane fuel cells, and finally the catalyst. We also try to replace the high costly PT catalyst with other form of catalyst like ruthenium or others. So you see the proton exchange membrane fuel cells here. This is the design structure. In the middle, you see the Nafion membrane is there. After, two part is there. One is diffusion part and another is reaction part, reactive part. So after that, one cathode plate and anode plate is there. That will combine. Then finally the output electricity will come on the top of the sections, and from the middle we got the water, which is side product. This is the membrane. Actually, membrane is how it's working. It has the SO3 group, which allow to pass H+ ion, but not the other material. So H plus pass through the membrane and it reacts with the other sides of O2, and then finally it produces the water and the electricity. So in case here, particularly we target treatment the cloths of the working electrode, then gas division layer preparations, then catalyst layer preparations, finally membrane treatment, and finally the electrode assembly preparations. So if you look this PTFE content, that means it is one type of doping which increase the hydrophobic property of the material. That means it repels the water and reduce the water accumulation problem in the fuel cells. So we optimized here the PTFE content to reduce the water management, increase the water management problem. Here it is the contact angle measurement which showing the hydrophilic property of the materials and is giving 20% PT is having high hydrophobic property. And this is the different sort of current contact angle measurement in case of the AH303 and PTFE content. If you change the PTFE content, how contact angle is changing and its hydrophobic property also changing. So this is the cloth structure on the cloth. This is nanostructured. Nanomaterial is deposited on the cloth, which PTFE amount. Then finally we check the gas diffusion layer properties. And here in gas diffusion property, we optimize the PTFE content and we fix the contact angle degree. And finally, on the carbon cloths, the PTFE carbon dust optimization we have done. Then here, this fuel cell performance we have checked. So by electrochemical setup, where the voltage and current curve is there, and finally the peak power we measure. Here it is the setup which we have done in our laboratory. All the instruments are fuel cells demonstrate cathode, anode, water supply, power supply, all are there. And finally, we check the performance of the fuel cells. And this is the cloth performance which showing it is high, the hydrophobic property of the material. And finally, the binder having very useful because of the reduce the pore and interact the each other diffusion and contact layer of the materials. Then here we take the performance which is having the C4 types of working electrode, which is acid doping HGPO3 and PAP PBI. Here we confirm that the PBI based material 180 degrees centigrade is giving high current. And for the PTFE content 20% with Nafion membrane is giving the cell potentials maximum. So in case of the fuel cell, we conclude that the catalyst layer with 20% PTFE looping carbon is giving the maximum hydrophobic property, and 180 degree centigrade increased the heat, PBI membrane showing the highest cell performance. So these are the nanostructural material which synthesis in our lab. Our next target in the future to deposit these types of nanostructures. We have to synthesis 1D, 2D, 3D, 4D, and this sub nano material we used to apply on the device of the fuel cells, water splittings, multiferric state memory device, and solar cells. So last conclude. Without help of this PhD student working in our laboratory, is the work yet not finished till now. They are working till now. So these 4 or 5 PhD students is working at present. And this is the sponsored research project which I am working right now as a PI. The 5 research project is running at present. And this is the collaboration with national, international collaborations we have with our laboratory. And this is my lab where the solar cells measurement is going on using the solar simulators, and my PhD student is working for measuring the electricity. And lastly, I thank my funding agency, ACRB, DST, UGC, and Calcutta University for supporting me for fund. Thank you very much.
Now I am requesting Dr. Ovi Mukherjee to give the vote of thanks.
There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There has to be a question and answer session first. There So if anyone has any question, they might ask Dr. Roy.
Ovida, your voice is not clear.
So Dr. Roy, if I may.
Yeah.
Uh, so I have noticed the solar cell.
Dr. Ovi Mukherjee, you are not clear. Your voice is not clear. Ovi Mukherjee. Dr. Ovi Mukherjee,
Hello.
your voice is not clear.
Okay, okay. Hello, Dr. Roy, can you hear me?
Yeah, yeah. I hear you. Okay, but very not loudly.
Hello.
Yeah,
There is some. I believe there is some problem with the connection. So it is
yeah.
a bit raining here.
Okay.
Anyway, if I am audible, then I would like to ask you. So
You
in
ask
case
me.
of your solar cell, I have noticed that you have used indium tin oxide coated glass as a platform. So as you
Yeah.
know, nowadays the focus is mostly on flexible electronics and so I mean, if something like PET or say suppose PDMS can be used as platform, I have seen the annealing temperature, so 80 degree, I think PDMS will be fine, but is the conductivity will be a issue here?
Okay. Actually, you are talking the polymer solar cells based, I think.
Yes, 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 yes.
Yeah. We have also have target to PVDF based solar cells. PVDF will
Mm-hmm.
be much better because it is having the both good property, electrical property. So in case of the PVDF, we in the top, the light, very good light sensitive material we can deposit also. And it's having the flexible property, good flexible property. If you check the literature, many literature is nowadays coming in the polymer, say polymer space solar cells, which is totally flexible in presence of the light also. Because when the radiation is coming,
Mm-hmm.
the radiation is falling in the fixed level. But in the polymer case, it can change the surface in presence of the
Mm-hmm.
light by sensing this. So it is our
Mm-hmm.
future target also making the flexible polymer solar cells.
Thank you. And I have also noticed that alpha hematite might have some very good biosensing capabilities if some protein or biomolecules be attached over it. People have already attached biomolecules over TiO2, so this might be another area of application you may look into.
That is the problem. Actually, biomolecule synthesis is very tough because our background is not support for this biomolecule synthesis. But also we have done the keratin synthesis and the chlorophyll synthesis from the leaves. So these two part already we have done, and then we check the solar cells efficiency also. But it is efficiency is not comparable with the perovskite solar cell. It is reach up to 3 to 4%. So we already done the keratin or chlorophyll, but other material we have to target to use for increasing the efficiency of the. Otherwise, people are not doing using these biomolecules as it is giving the low efficiency.
And I also know your student Orho personally. He's my
Yeah,
junior
sure.
in science college. It is nice to see his work getting recognition, and I thank you for that. I would also love to visit your lab once the COVID situation is
Oh,
over,
sure,
and
sure.
we can discuss regarding if some collaborations can be done. So,
Sure, sure. It is good.
Mr. Mr. Gayan, so,
Any other questions from student? Actually, they understood the working principle of these four. Then it will be. I'll be happy.
yes, sir. I
If,
mean, yeah, the thing is, we are trying to get nanotechnology research with advancements in chemical engineering,
okay,
nanotechnology, polymer composites in the syllabus. It is not covered right now. We only teach ceramics and petrochemical as elective, but these things we are
okay.
talking. I mean, there is a talk in the council to get these interesting things, and maybe in the future we can send some of our students to get trained in your lab in the
Sure,
basic
sure,
chemistry
sure,
and
sure. The
so.
fabrication process of the solar cells, multiferric or thin film depositions, nano thin film, I can teach them. No problem.
That would be a great help. Mr. Gayan, if you may now, I think there will not be any question from the students, unfortunately. So,
Am I audible?
Yeah.
yes, yes, you are.
Uh,
Yes, sir. For your
yeah.
thank you for your nice presentation and kind cooperation. We can learn much more from you, sir.
Thank
And
you.
I hope if our students have any question, please ask to sir. All of you have any questions?
So I think there will not be any questions from the student side. They have all gone silent. Anyway,
They can ask the chat box also.
Hello, sir. Sir,
Yeah.
I have a question.
Yeah.
Is there any application where this technology are used? The technology are using now
Which technology?
like
Nanotechnology.
nanotechnology and
Ma-
huh? And in
Many of the field, many of the field nowadays, nanotechnology is working because
acha,
if you see, yeah.
hello.
Do you heard the nano paint,
Okay.
nano fiber synthesis cloths? All are working in the nanoscale level. Nanoscale level means one of the dimension it should be below 100 nanometer. That means 1D, 2D, 3D, any of the dimension should be nanoscale, below the nanoscale, nanometer range. So many of the people are working, particularly lab on chips, electronics field, um, textile industry, all are working on the nanoscale level also, and particularly optical property, optical scale, using the carbon nanotubes or carbon related material is giving the very high sensitive gas sensor or other magnetically actuator.
Okay, okay, sir. And in solar panel, this technology had started using.
Yeah.
Okay, okay, sir. Thank you.
okay, so I would like to thank Dr. Roy for his wonderful presentation and illuminating us with newer sides of the technology, recent advancement in chemical as well as nanoscience. I hope everybody has learned a lot from the talk. I would also like to thank the chairman, Dr. Praveen Maiti, for taking out time from his busy schedule and overseeing the proceedings of the talk. I would also like to thank my colleagues, Mr. Aman Ghosh, Mr. Shoman Kantikayan, and Mr. Pradipto for their hard work. Without them organizing this webinar would not have been possible. I would also like to thank the students who have joined, and the feedback form is given in the chat box, so kindly fill it up and you will get a response then, and your certificates will be sent to your
Thank you.